Shall we begin now?
Yes, we can start, and let others join if they are joining in between.
Okay, okay. So today is the ninth session of the program. I welcome our resource person, Professor Vishnu Nambudiri, and all of you to this session. Over to Professor Vishnu Nambudiri.
Thank you, ma'am. I think till yesterday we were able to discuss various things related to using Python programming for mathematics computations. And yesterday we have seen some peculiarity of computer software in drawing functions, and we saw how to actually solve certain issues when we are trying to deal with some discontinuous functions. But we haven't said actually that how to determine if a point is actually a discontinuous point or not. And in fact, we were trying to use the epsilon delta definition itself for locating if a point is a point of discontinuity or not. Not exactly in the mathematical sense, but to some extent. Okay, today, continuation of that, we are going to deal with some functions available in Python, which will help us to do some basic calculus. Okay, so basic calculus actually starts with finding limits, and afterwards checking continuity, checking differentiability, if possible, find the derivative of a function. After that, try to integrate. All these things are part of basic calculus. So we are going to do, we are trying to understand the basic functions available in Python for performing these calculus related operations. I have already shared the Google document link with you where I will be copying and pasting the code that I am typing in my Spider interface. You can open your Colab interface as usual and you can experiment with the Colab interface. I'm starting sharing my screen in Spider. So my Spider window is here and we are going to do some basic calculus using symbolic Python essentially. So we know that symbolic Python actually helps us to define symbols. Okay. So the very first thing that we are going to do is import the symbol command symbol function from the that sympy module from sympy import symbol. As I told, symbols also can be imported if you want to define multiple functions. Since we are going to deal with the limits and only one function is actually involved in this, we are only using symbol. Okay, that's important. Now, after that, let us create a symbol. X is equal to symbol X. Okay. Now, the first thing that we are trying to do is finding out limits. To find out limit, let us try to find out the limit of a function. Let us define. No need to define. We can straight away take it. So for that, we need to import limits also. Limit. That's a function name. Now, trying to find out, or otherwise, let us store this to a variable L limit of say the function 1 by x as x tends to say 3. So we should read it as limit of the function 1 by x as x tends to 3. Print that. Okay, we need to save it. Saving, running. The result is just that the limit of 1 by x as x tends to 3 because sympy is actually storing this limit inside the variable L. It might have already computed, but the result is not visible here. For the result also to be visible, we should instruct that to do this computation. Do it. Let's see now. The result is 1 by 3. Or maybe here itself. The result is 1 by 3. Here itself we can try. And maybe, in fact, here itself. That's it. Now trying something else. 1 by x square as x is 3. 1 by 9 as x is 0. It says infinity, which is not entirely, which is yeah, entirely correct, because there cannot be minus infinity, because x square is always positive. Let's try with x. X also it says infinity. It's giving only. I think it's giving actually the positive limit. Okay, let's try to see how to evaluate. Sorry, right hand side limit. So let us see how to evaluate right limit and left limit separately. After that, after some time, after experimenting with some more functions. So sine of x, but for that we need to import sine from sympy. Import sine, then sin x is 0, cos x is 1, maybe log, and exponential, minus infinity, 1. All these things are possible. To find the positive limit, now, for example, finding one-sided limits. Same function I'm using, but with the extra option, direction equal to minus infinity, direction equal to plus infinity, log x. Will it work? It's giving the limit to be minus infinity, but that's not completely correct, because log x, it cannot go to 0 from the minus direction. Somehow the answer doesn't seem to be correct in this case. Okay, that's fine. Now let us try with absolute value. I don't know whether absolute value actually exists there. Mod x by x as x is 0. So mod x by x, if as x is 0, if it's from the positive direction, I should get what's happening. Cannot import absolute value, then I think absolute value is not really necessary from this function. Directly also we can evaluate. To identify from where it's coming, let me put it like this. Okay, now trying with minus 1. Okay, that's minus 1. So it's giving the answer. So we can evaluate limits like this. Now infinite limit also can be evaluated. Okay, infinite limit also can be evaluated, and for evaluating the infinite limit, we need to use the infinity available in a special class called S. Okay, special class called S. from sympy import capital S and S infinity. S contains infinity. For example, dir S. If you try dir S, sorry, one print is also required. We are getting several things like what are the things available there. PI is there. I don't know what this PI is. Rationals. I think it must be the set of all rationals is a part. I guess golden ratio is a number. So infinity is it there somewhere? Gatlin. Infinity is there. Okay, infinity is also here. So we can use S dot infinity in that case. Okay, let's try to find evaluate infinite limit. Limit uh, 1 by x as x tends to infinity in the positive direction. Okay, why is it giving an error? In okay, INFI it's capital. So 0. Or even if you do not specify the direction, it's going to be 0. Even otherwise, maybe even 1 by x plus x infinity minus x minus infinity. But infinity in Python is represented using the symbol minus and OO. But minus and OO, I don't think that it will directly work. You need to just give it like this only. OO, I don't think it will work. Okay, let us try anyway. No, that's not. This is not correct. Even though the representation of infinity given by Python is OO, we cannot straight away use that. That's not possible. Okay, let me just update Google document with this. The entire limiting exercises that we have done. The link is here. I think the link I have already shared in the Google Meet. Yeah, that's already there. You can try. Okay, that's all about finding limits. Now we can actually use this finding limits function for checking if one particular function is continuous at some point or not. Okay, so but the most important thing is that we cannot check the continuity unless we know where exactly we have to check. Okay, the point which we suspect to be discontinuous, we should identify first. So that process is, it's somewhat manual. But otherwise, you can use that NP diff, and so that you can determine that if some huge difference is appearing somewhere, and probably in that way you can try to locate some point to be discontinuous, and you can check also. But that technique is, I don't really think that that's going to be much useful, because continuity cannot be checked like that. And for checking continuity, I think we already have several tools. The most important one being our own experience, right? So continuity we usually check using our own experience, because we, if we already have a collection of functions of which the continuity properties are known to us, the places where it's continuous is known to us. For example, we know that polynomial functions are continuous everywhere. We know trigonometric functions, wherever they are defined, we know that they are continuous everywhere, provided they are defined at some particular point. And log x, we know that it's continuous after its definition. After its definition in defined interval, it's continuous. These things we know. And most of the functions that we are going to encounter, mostly what happens is that those functions are combinations of these functions. Mostly, I'm not saying always, most of the times. So we will be mixing up polynomial function, we will be mixing up polynomial with trigonometric functions, the logarithmic function, exponential, and sometimes we will be mixing in such a way that the functions are defined in a piecewise manner. In that case, we know that the definition needs to be checked. If we have a piecewise definition of functions, and if the if pieces are continuous, then we know that the continuity needs to be verified at where the pieces join. Okay, these things are known to us, and because of our experience in dealing with the continuous functions, we will be able to make out good decisions regarding if a function is continuous or where the continuity needs to be checked. That thing cannot be actually completely left to Python. That's not quite possible, because it's a programming language. It does not have that much experience as a regular mathematician or a professional mathematician has. So you need to definitely depend on your experience to determine which point to be checked for continuity. Okay, but after determining which point to be checked for continuity, Python can be helpful to you. Okay, computer can always handle only finite data, but human mind is not exactly like that. Human mind can convert infinite data into finiteness by means of experience. For example, we know that the function modulus of x by x, the function modulus of x by x, we know that that function is continuous everywhere except at 0. Right, because as x is 0, what happens is that left side we will get -1, right side will get equal to 1. So 0 is the point where the problem happens, and we need to check only the continuity at 0 alone. Other points, it's clear to us. But in the case of a computer function, what happens is that if it tries to take the sample data and tries to check the limit, then the problem is that it may miss 0, and it may check left side of that and right side of that. Okay, in that case, it's difficult to trust the computer program for verifying the continuity of the function. You should not blindly trust any computer program for checking the continuity. Okay, continuity is better judged by a professional mathematician. So anyway, using this limit function, we can define a function to be continuous or not. We can find out a function to be continuous or not at a given point. Let us try to do that. It's very easy. Okay, now I'm copying and paste. Okay, now I need to copy and paste. I'm starting a new program for checking continuity. This is 40. This would have been 43. Okay, 44. Or continuity check. Suppose that we have a function. Which function we have? We cannot define it exactly like f of x equal to something, because that f of x equal to something, if we are putting that x may not be a symbolic variable, that can create some trouble. So let us just take f equal to x by mod x itself, absolute value of x by mod x, where x is symbol. Of course, we need to then import sympy, import symbol x equal to symbol x. That's defined. Now, absolute value of x by x. What do you need to check? You need to check c equal to 0. We are going to check the continuity at 0. So, what are the essential things that we have to check? So, very first thing we have to check is that f of, or we need to substitute, we need to find out fc. So, for continuity, we know that there are the conditions that we have to verify are left side limit should exist, right side limit should exist. Both these limits must be equal. They must be both must be equal, and finally that both these limits, the equal limits, must match with f of c. Okay, the function value should exist at c, and we must be able to evaluate f at c. Okay, evaluating f at c, for checking that thing is a little bit difficult. Not difficult. That needs some extra thing that we need to understand. I'm not going into that. I'm simply assuming that f of c actually exists, but in this case, f of c is not going to exist. Okay, FOC, if I try to evaluate, maybe I should use some other function instead of this. Which function should I use? This function is a little bit complicated because FOC I cannot definitely evaluate. Absolute value of x by x is not possible. So some function which is evaluatable but limit does not exist. Which one should I take instead of absolute value? Uh, Okay, maybe I can choose the function, the piecewise function, the replace function. It's sorry, the signum function itself I can use because it's -1 and +1 at different points. So I can, but I don't know how to define the piecewise function using symbolic functions. Is a little bit, it's complicated issue. So how do I define even that using symbolic functions is the question. Maybe what should I do otherwise? Okay, signum function. How do I define a function that's defined, a standard function that is defined at some particular point, but not continuous? How do I do that? Till mod x, sin x into mod x is not going to work. Mod x itself is anyway continuous. Which function should I? Okay, let me just see. Okay, so let me just try to. Okay, let me just try to find out what exactly the symbolic Python is saying if I'm trying to evaluate this. Okay, let me just try to do that. So for evaluation, I should substitute. I think substitute. I need to. Need I use substitute like that? Okay, let me just try. F dot subs 0. F dot subs x 0. Okay, it's giving nan. Okay, let me just once again try. Is it nan? Where should I? So if I am able to check, this should have actually worked, but this is not okay. I have not imported sympy as it is. Okay, that's the problem. So let me just import nan also. Nan stands for not a number. Okay, it says true. Therefore, in this case, I know that the evaluation is not going to work. If the evaluation is working and if the evaluation turns out to be a number, that's fine. Okay, so this thing also we need to check. That's the only way to handle this 0 by 0 situation. Otherwise, the problem is that it will create an error and the program will completely stop. The program will completely stop if you try to evaluate otherwise. Print f substitute for x equal to 0, just substitute. If we try to evaluate, it will show, it will give you the answer that nan. So you need to check for nan, and of course okay, of course you can check against this nan also. Evaluate the left limit, evaluate the right limit. If all these things are turning out to be nan, then it's a little bit of trouble actually can be there. Okay, let's try to see such a situation later. Okay, anyway, so nan is important. Now the thing we have to check is left limit. Left limit is defined to be, so we need to import limit also. Left limit LL equal to limit of the function f as x tends to 0 in the direction equal to minus. Left limit is here. Now the right limit is defined in the same way. Right limit is this plus, and it's here. Now the f value at c equal to, suppose let us check this to be equal to, this is anyway getting evaluated. This is equal to nan. That's the only problem. Okay, so we have all these values. We have all these values with us. Now what we need to check, if any of these two things are, if all these things are equal, then we will say that the limit exists and the limit is actually the f value. Okay, if left limit equal to right limit and these two are equal, right limit equal to f value, and remember that we should check for nan also, because it can happen that left limit is nan, right limit is nan, f value is nan. In that case, we cannot accept it, right? That's not acceptable for us. And RL not equal to nan. That also we should check. Because if we are getting all these three to be equal but equal to nan, then we cannot accept that to be the answer. Then print f continuous at c. I think that's it. Else, we should have an else clause also. Else, what about one? Oh, at one also it's giving like that. Yeah, what is the question? Please.
Here we should not check that limit because not equals to infinity also.
Not equal to? You are asking if infinity is allowed or not, right?
Not equal to infinity should not be checked.
No, we are not. We are not accepting if a function is continuous. See, f of c equal to f of c equal to infinity is not allowed to be. It's not. It cannot be continuous in that case, right? It has to be a real number, isn't it? So the function to exist at a point, it must be a real number. It should not be infinity or not a number. It's not allowed. Was that the question?
The limit may be infinity. If the infinity equals 10,
What you're saying is limit can be infinity. So you want infinity to be
yes, sir.
you want the infinity to be accepted as a correct answer for all the if all the three values are equal to infinity. Do you want to say that f is continuous at that point?
So, sir, if the limit is infinity, I should neglect that one. Because that will be discounted.
Okay, if the limit is infinity, okay, let us try to see. For example, suppose that instead of f is equal to absolute value of, let us try to take f to be equal to 1 by x. Okay, and take this to be equal to 0. Let us print the values. Print RL, LL, F value. Oh, but we forgot to do it. That's why probably it's giving. Okay, sorry. That's why probably it's giving the error. Let us try to evaluate. So what is this? Z O O F value obtained on substituting absolute value of x by mod x. That also stands for infinity, but according to the definition, it says that OO and minus OO are infinities, but ZOO is a complex infinity. I don't know why. What is exactly meant by the complex infinity? Maybe it's infinity without having any direction, left or right direction. But why that should appear here? Absolute value of x by x. Why should that be equal to complex infinity? I don't know why it's happening like that. Okay, these are the three values that we are getting. These are not nans. So what you want to say is we have to check. We have to check this infinity also, right? Is that you are saying?
Yes, sir.
Okay, so thank you. That's right.
The limit is infinity.
Right. Then instead of we need to add an extra condition also, right? And
I think so.
one of these limits is not equal to RL not equal to yes, RL not equal to s dot infinity. Only one needs to be checked because RL and see all these things will be checked. See these only after checking the first three conditions, the last two will be checked. So it's enough to check only RL and RL not equal to. I think minus infinity also needs to be checked. So how do this check will happen? Left limit equal to right limit. If the left limit is not equal to right limit, then this will not be printed. Okay, if the left limit equal to right limit, but right limit is not equal to f value, this will not be printed. Continuity will not be accepted. If the first two are equal, but still right limit. Oh, sorry. First two must be equal, and RL should not be. If RL equal to nan, then also it will not be printed. If RL equal to infinity, then also this will be printed. This will not be printed. If RL equal to minus infinity, then also this will not be printed. So if all these conditions are together satisfied, then only it will be printed that it's continuous. Now let us try to see that once again. Not continuous at 0, 1, but still it's giving. Why is it like that? Oh, sorry. I have not used C. That's about C. Okay, instead of C, I am straight away using S. If it's continuous at 1, not continuous at 0, values are 1 minus 1 and NaN, not continuous at 0, continuous at 1, maybe instead of that, F equal to, let me import sine of x, sine of x by x, continuous at 1, not continuous at 0. Is that correct? Sine x by x. So what are the values? Sin x by x, we know that left limit turns out to be equal to 1, right limit, so because limit is actually 1. But what happens is that sin x by x, sin 0 by 0 does not exist. It's NaN, so not continuous. So this function actually tells, this function actually can evaluate if a given function is continuous or not at a point. So we have taken care of number not existing case and number existing but infinity case and minus infinity case. All these cases are handled. I think this function is, the program is good enough for checking if a given function is continuous or not. Okay, let me copy and paste this to Google document. So it's updated, you can try. So we can actually convert this into a function, right? So checking continuity at some point C, we can convert this into a function. This is a complete program, entire program, not a function. We can convert this into a function. You can just try it. That's all about checking continuity. I think we can even evaluate, even check. We can check the continuity or limit on multivariable functions. Also, we can do that. So let's try to do that. Limit multivariable. So let us import symbols xy equal to x and y defined to be so. Now let us define f to be equal to x square plus y square. We know limit also needs to be evaluated. Limit also needs to be imported. Limit. I think that's it. So limit of f as x tends to, I think only one can be evaluated. If you want to evaluate multiple, maybe you have to do it 2 times. X tends to 2. So y square plus 4. That's evaluable. So multivariable is also handled like that. Multivariable, the only thing is that you need to clearly specify that depending on which. So if you want to evaluate using the other limit also, what you should do is that you should apply this limit multiple times. I don't think that you can apply it simultaneously. maybe you can already this limit is found. Now without evaluating, I think you can directly do y to 2 and apply the do it only as a final step, so it's working. So do it can be done, do it can be taken care of towards the end before evaluating in the beginning itself. So the Google Sheet is updated. Now in the same way we can find derivative. Okay. So same way we can find derivative also. Let me start a new file, 46th one. From sympy import symbol derivative. X is equal to symbol x define a polynomial x cube plus 3 x square plus 1 print. We already imported derivative of polynomial with respect to x, and once again we need to do it. 3x square plus 6x, or even directly we can do x square plus cos x, but cos x is not imported, sin x. Or partial differentiation also can be like done in the same way. Same command should work. Derivative of x square plus xy with respect to x, 2x plus y with respect to y. And now evaluating the derivative at some particular point, what you should do is that you should just put after doing you should substitute subs which one to be evaluated, subs y 1 Why is it printing 2x plus? Okay, one second. 2x plus y. Okay, 2x plus y. This is first derivative. Derivative with respect to x. This is derivative with respect to y, and this is derivative with respect to y at which value? At 1. Differentiating with respect to x is this, y is this, y at 1 is evaluated to be, y at 1 is evaluated to be just x itself, because there is no y present in that, or otherwise you need to evaluate at x and substitute for x, y plus 2, because it's 2x plus 2, x is substituted with 1, so it's getting y plus 2. So evaluation also can be taken care of like this. So this is how we differentiate, and multiple times differentiate. We can even give product of functions we already see. Okay, that's not really important here, because we can calculate the product of functions also like this. Product rule, quotient rule, etc. will be taken care of automatically. Like derivative of suppose that we define it to be x square by sine of x. So derivative of the product function with respect to x, and do it. So the quotient rule, everything is taken care of automatically. Sin x square plus 2x by sin x, because so what might have happened here, sin x into, okay, one sin x is cancelled, that's it. Let me update the Google document with the correlated derivatives. Now, for finding the higher order derivatives, either we can apply the derivative function multiple times, or we can specify which order we want as the third parameter. Okay, for example, Suppose that we want to of this polynomial derivative, this polynomial. This is 1 times. Either you do it derivative, and then okay. But in second time also you should specify x. You do it like this, or you may specify the third parameter, second derivative. Both these work. Okay, now let us try to do a problem using this derivative, etc., that we have found. So, derivative is actually very useful, especially in calculus, for finding maxima minima of function, right? So, local maximum, local minimum can be found out using the derivative technique. We know that local maximum, local minimum, etc., exist at points called critical points. Critical points means either the derivative does not exist there, or the derivative is equal to first derivative is equal to 0. Okay, so we need to check the points where we need to solve for the first derivative to be equal to 0. So solve is one function that we are going to use. We need the derivative function. After that, we will check if we will check the critical points, and we will try to see these critical points are actually what do you call, are they going to give maximum or minimum. Okay, and even for checking the maximum minimum, we can go for the second derivative test as well, just to see if they actually give you the maximum or minimum. Okay, so let us start doing all these things by using a problem in calculus. So next problem, we are trying to deal with the problem of finding local extrema, and therefore finding local global extrema also, because we know that global extrema exists at local extrema points, and where local extrema is existing, and of those local extrema, whichever is the maximum is the global maximum. Of those extrema, whichever is the minimum is the global minimum. You know all these things. So let us start a new program. Let me just once again update the Google Sheet with all these. Okay, updated so. This program name is 46. So let me just okay, now it's updated correctly. Okay, next problem is to check maximum minimum. 47. Find extreme. So recall the second derivative test for finding local maxima, local minima, etc. So once a critical point is found, okay, once a critical point is found, the local maxima can be that particular point is a local maxima, provided that the second derivative is zero and sorry, the first derivative is zero, and first derivative is zero means critical point, and the second derivative is less than zero. Okay, in that case, it's a local maximum. If, on the other hand, if the second derivative is greater than zero at this particular point, it's a local minimum. Okay, if the second derivative is equal to zero, then it's a point of inflection. Okay, there are three things. So the conditions are that first derivative is zero, second derivative, if it's less than zero, then local maximum. If it's greater than zero, local minimum. If equal to zero, point of inflection. So three conditions. These are the three things that we want to check. So let us take an example. Let us define a function and try to do all these things. Suppose that we define y to be equal to. We are just going to deal with one symbol. So from symbols, sympy, import symbol, x is a symbol. Let us define y to be a function 5x cube minus or plus 2x square minus 3x. So this is the function we have. And if you want to see this function in action, maybe we can use the plot. Okay. So how did we use sympy plotting? I think sympy. So we need to import plot and okay, directly sympy plotting. We need to import plot. Import not sympy, from sympy plotting. Sorry. Import plot. Let's try to plot y. So this is the function. Okay, for the time being, I am suppressing this plot. Now trying to find out the points which are critical points. See that this particular function, from this plot we can identify that minus 10 to 10 is actually a safe range for evaluating local maximum minimum, because we can actually see that there is actually a point of inflection somewhere in the range. I don't know exactly where it is, in minus 5.0 to 5.0. The direction is getting changed. The concavity becomes convexity. Therefore, the point of inflection is certainly there, and critical points are also there. And there is no point where the function is not existing, or even the derivative is not going to exist. So Critical points are those points where the derivative is going to become equal to 0. Okay, so we need to import solve. Solve is now imported. Now let us try to see the solutions of y dash equal to 0. So y dash, so I cannot label y dash because dash is not a valid character in the variable name. So y1, let me call it as y1, or y derivative, or dy instead. I think that's much better. Dy, first derivative of y. Dy is derivative of y with respect to x, and do it. Let's see what this dy is. Oh, derivative is not important. So the solution is here. The derivative is here, 15x square plus 4x minus 3. But dy we need to equate with 0 and find critical points. Solve dy. Dy equal to 0 essentially. And printing the critical points. So minus 3 by 5 and 1 by 4, 1 by 3 are the critical points. Let's try to find out the second derivative. Find second derivative. So d dy it is called. So the only thing is that you don't have to differentiate dy once again. It's not necessary. Y with respect to x 2 times. That's enough. And now check the value of d dy at critical points. For critical point, let us call it to be C in. So there are 2 points. So how do we check that? The value of d dy we have to check, and we need to substitute if d dy dot substitute C. What should we say? It should exist because second derivative is also polynomial. We know it can be equal to 0, of course. If it's less than 0, we will say that C is a local maximum. Else, elif, not else, elif. There is a condition, of course. The condition is that if it's greater than 0, it's a local minima, or if none of these, or why is this happening like this? Wind is already here. Is there any indentation problem? Let me correct the indent. It's a point of inflection. Okay. So substitution is for x. There is no point of inflection. Oh, sorry. So the sign of the second derivative we should actually check. Instead of checking this, the last thing is actually not correct. So we should have checked. No, let us remove this. The point of inflection we should say. What should we say exactly? The sign. How do we find out the sign on the left side? So the critical point. So what we need to check is if the function, if the derivative is changing its sign, if it's becoming so increasing to decreasing, decreasing to increasing, sign change we should check essentially. So what essentially we need to check is in the interval. Okay, so we have. Let us try to see the plot once again, so that we can easily understand what's happening here. So where is the plot? We just enable that. So we have located the points to be, what are the points? So minus 3 by 5 and 1 by 3. Minus 3 by 5 is essentially 0.6. So at 0 point, minus 0.6. At minus 0.6, so it's somewhere here. Minus 0.6 is somewhere here, and 0.33. So at these points, we need to check. See, we can say that the function is coming down here. Now it's moving here, and it's again going up. So it's coming down slowly. It's increasing, 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 and it's now decreasing, and now again increasing. So you can see that something is happening somewhere in between. So how do we locate the point of inflection? That's the question. Okay, let me update this much the Google document first. So if someone is interested, they can try up to here. There is a problem with the indentation here once again. So you need to be careful about the indentation. So just before this critical point, we need to check if what is the sign. Just after that, we need to check what is the sign. Uh, if the Okay, let us see where this second derivative is. The second derivative is becoming zero at some point. We need to promptly check. Okay, if the second derivative is becoming zero at some particular point, that point is the point of inflection. But for confirming that point to be the point of inflection, we need to check the left side and right side. Okay, the left side and right side of that second derivative, we need to check for the change in sign of the derivative. Okay, let us try to see that. So here the second derivative is here now, but here, okay, let us try to solve the second derivative where the second derivative is becoming zero. Let us try this. Point of inflection or possible points of inflection is obtained by solving second derivative at zero. Okay, so if we try to solve, I was checking the first derivative. I need to check second derivative. Second derivative is r. Okay. So the point of inflection possibly is at minus 2 by 15. Minus 2 by 15 is how much? So minus 2 by 15. So minus 4 by 30. So 4 by 30 is roughly how much? 40 by 3, it's 14, 1.4, around minus 1.4 somewhere. Around minus 1.4 somewhere here. Okay, so let us try to check if it's actually a point of inflection. So since there is only one point, we need to only check the left and right of that. If there are multiple points, the problem is that we need to choose the points where we are evaluating the second derivatives. Suppose that we have 3 points. Okay, suppose that we are getting, or 2 points. Suppose that we are getting 2 points where the second derivative is becoming zero. Suppose that the first value is at C1 and second value is at C2. Now the problem is that we need to check the interval minus infinity to C1, C1 to C2, C2 to plus infinity. So we need to choose points to the left of C1 in the interval C1 C2. Okay, in the interval C1 C2 and after C2. But here there is no such confusion because there is only one point where the second derivative is becoming zero. Okay, so which is that point? There is only one point. Even for checking one point to be safe enough to choose a point within that interval, we don't know if you are changing the function, we may get more than one point. So uh, we need to find out if more than one points are there. We need to find out the difference between consecutive points, and we need to choose the minimum of that, and then we can take the minimum of the distance between the points. For example, suppose that we have critical points 1, 1.2 and 1.5. So we need to take values to the left of 1 in the interval 1 and 1.2, in the interval 1.2 and 1.5, to the right of 1.5. So how do we choose carefully a point between 1 and 1.2 and 1.2 and 1.5 safely? So we need to take the difference between consecutive points, and the least of the difference we can take it to be, we can subtract from the right endpoint least of the difference or half of the least of the difference, so that we will safely remain inside the same range. Okay, all these things are going to happen if we have more than one possible points of inflection. But here there is only one point of inflection, so we don't have to worry about that. So, but anyhow, okay, let us see this example, same example with one point. After checking one point, we'll go to an example where we have more than one points of inflection, more than one possible points of inflection. Okay, so how do we check? What is the thing that we have to check? We need to check if it's greater than zero, or if the signs are different, essentially, right? So how do we check if the signs are different? So maybe we can define the signal function if required. That's much more easier. Define is gn of x to be if x greater than 0, okay, we will define SGN to be, okay, we are taking to the left of that. So we can be safe, we can safely assure that we are not going to actually get anything equal to 0, because we are checking to the left of a solution, to the right of a solution. So on the left and right, we are choosing point in such a way that at that particular point, the value is not 0. Okay, x greater than 0, return 1, else return minus. Let us keep this, okay, here itself. So now going to make use of this. For points of inflection, let me call it to be pi in possible points of inflection. If SGN of the second derivative I should test dy, so substitute, which point should I think I will take for the time being, for to solve the issue, let me just take epsilon to be can we use np diff instead of that, from numpy import diff. I don't know whether it's going to work on this this particular. This is a list, so it should probably work. Epsilon equal to a list of the differences that we want. If there are more than one point, diff difference in possible points of inflection and the minimum of that. Okay, I'm just experimenting with this. So for the time being, I will put this to be a list consisting of the values. I'm just experimenting. 1, 1.5, 2.5, 2.7 or 6. I'm trying to see this diff commenting out the remaining. Trying with it. So possible points of inflection 0.5. What are the values I'm getting? Differences 1 to 1.5, 0.5, 1.5 to 2.5 it's 1, 2.5 to 2.6 is 0.4. So we can choose the least of this and take epsilon to be least of that divided by 2, so that we can be safe enough. So we can stay inside the open interval itself. Okay. If signum of sine of function of what should we substitute? So to the left of that we need to check, and the right of that we need to check. Left of that point is going to be pi. Oh, pi is actually pt in point of inflection. It will be called pi is pi. So there is a confusion. So left side of this minus epsilon. Not equal to. Okay, let me just see if I have completed. Okay, now I have completed. Not equal to plus. So what I'm trying to do is I'm trying to take a value to the left of the first point of inflection that I have chosen, minus epsilon I'm taking. So first point of inflection, for example, it's 1. So I'll be choosing 1 minus the least. The difference between the values is the minimum is 0. So 1 minus 0.05 will be chosen as PTL inflection minus epsilon. And to the right of that also a point is chosen, and the sign of that is found. Okay, just to see if the signs are different or not. That's it. So if the signs are different, then what should I print? Print this particular point is indeed a point of interest. That's it. Substitute. Once again, same mistake I did. What should I do? Here it is for what? X. Oh, sorry. I think because there is only one value, the difference is turning out to be what is the difference? Is there any difference at all? So there is no difference. So I need to take epsilon to be okay. I need to be a little bit careful. If there are more than one values, then only I need to take the difference. Okay, otherwise it's not necessary. If more than one, then only I need to choose epsilon to be this. Otherwise, I can choose epsilon to be anything. There is no problem because uh, if there is more than one point, then only I need to be careful about choosing the epsilon in such a way that it will not cross the boundary of that interval. Okay, so else I'll choose epsilon to be just equal to one. Okay, now probably I think I could solve this problem. Okay, I think okay, one more thing. So instead of the plotting available in sympy, I will try to use the plotting available in matplotlib, so that I can safely use numerical Python related stuff, and some more extra plotting options are available in matplotlib. Import matplotlib pyplot as plt, and I will use plt dot plot plt dot show. Convert expression to, okay, I need x and y coordinates here. Sorry. So how do we find x and y coordinates? Where are the x coordinates? Where are the y coordinates? Where is this x? Okay, y is this? I need to evaluate y at certain values of x. So let me just check x coordinates to be something in the range where I was getting all these things, maybe some -5 to 5. Import in P. So let me create some linear space between -5 and 5, some 100 points. So these are the x coordinates. And what about y coordinates? Y coordinates can be created So using the linear space, I can create the y coordinates. So what should I do exactly? So let me create it as an array. Y dot subs for x coordinates. Substitute for x value in for x in no x value in x. So what is happening here? Finally, y coordinates are now created. Substitute x values should be substituted for x, where x values are from this. Okay, let me just try to see x coordinates and y coordinates. Plotting will be done later. Okay, anyway, x coordinates will be definitely found. The only worry is about y. Linear space is not defined. Okay. Probably it's true. Minus 5 to 5, is it really necessary to use minus 5 to 5? It's too much, it seems to be. But anyhow, okay, it needs to be too much. There is no other way. So since the points of inflection, okay, let us minus 5 to 5 is anyway used. That's not a problem. Okay, okay, this is anyway working. So we can plot now. Plot x and y. And show. This okay. Minus 5 to 5 is here. Now let us plot the critical points as well. Critical points and the corresponding x values. Okay. Critical points are already there. Where are the critical points? Critical points and the points of inflection also. So how to plot the critical points? What are the critical points? Here and there. Y corresponding to critical points is once again substitute the same. So y value corresponding to critical points. That's it. And plotting. What are the things to plot? X coordinates, not x coordinates, critical points and corresponding y critical points. And let us plot it as, let us define the style to be a red square to easily distribution. So these are the critical points. So if you want to mark the corresponding points on the x-axis, suppose you want to mark the critical points on the x-axis, then instead of uh, x-axis, so instead of that, you need to probably use 0. So okay, critical points and not y substitution is not required, just 0 is enough, because 0 for x value in critical points and b dot, what is b dot? B dot is not appearing. B, what is for diamond? I think diamond D. Uh-uh. So what's happening here? Critical points, 0 for x value in critical points. So I'm plotting x is here. Okay, same thing I will try. RS itself. So let me just try to create 0, do it separately. So what are these? So corresponding to critical points, I need just 0. That's the only thing I want to create. I'm trying to create. Nothing else. So 0, 0. There are two critical points and 0, 0 is appearing. That's quite fine. Why is it not working there? Okay. So x is here, y is here. Maybe because it's on the axis. The axis is removing that probably. So instead of y equal to 0, maybe I can put it to be 0.1 to just to see that. Oh, I think it's. Okay, okay. This is very close to. Okay, let me just try to make it slightly minus 2, 2. And let us try to suppress even this. So that, okay, it's there. It was there, but the problem was that it was below the critical points. That's the problem. Okay, because the scale is too large. You can see that the scale is the plotting is from minus 20 to 40, and all these things are happening in a very narrow region. Okay, minus 1.5 to 1.0. Let me just put minus 1 to 1. It's slightly better. The blue, it's a blue square now. Blue diamond or blue plus. Okay, that plus is appearing. Now let me just try to make even this. Yes, that's what. So the critical points are or critical values, not critical points. Values are marked with plus, and critical points are marked with this red square, and the points of inflection also we can mark similarly. So to mark the points of inflection, where are the points of inflection? The points of inflection are possible points of inflection. So they are points of inflection. So we don't have to worry about that. Otherwise, we can create a separate list by filtering out non-points of inflection. But here it's not necessary. We can straight away do that. Possible points of inflection. Those are x values. And what are the y values? So y values we can evaluate. So let us prepare a. So this is the point of inflection. You can see that a cyan dot you can see that's a point of inflection. Maybe we can change the line width slightly so that the point can be. Okay, let me just try to change the line width. Now change to ignore line width. Maybe I can do it separately somewhere. Just see that plt dot plot. No, plot is not going to work. Line width equal to, that should actually work, but somehow it's not giving me the actual result. Line width equal to, uh maybe I should do that much before. What happened? Okay, let me just try to change, because is it because single point is there? Let me just try to change the line width in something else. Plot, maybe PLT here itself. I should do that. PLT plot. Let me try to do it in the first plot itself. Line width equal to 5. Here it's getting changed. Maybe because I think only with the line it's working, not with 2 points. 10. It's fine. It's because only 2 points are there. It's not. It's line width. Maybe that the square is not being considered as a line properly. So maybe if I change it, oh, okay, here it's working. But here it's connected. Okay, these two lines are connected. So this is something that we don't want. That's the problem. Okay. On the other hand, what can be done is, instead of this, marker size can be changed. That's probably, if we change the marker size. It's. I think this is giving. I don't know. This is giving somewhat desired results. Okay. This can be used for changing the size. Okay, so the points of inflection is marked. It's here, cyan dot. Red diamonds are critical points, and the points corresponding to that on the x-axis is also marked with plus. That's it. So let me update the entire Google document. This is starting from where program is 47. So the entire program is updated in the Google Sheet. Okay, I think we could complete the maxima minima problem here somewhat incomplete, and not only that, we were able to see the how this thing is working, how that the plotting for the plotting functions can be actually made use to understand the problem somewhat efficiently. Okay, that's also there. So limit can be found, continuity we checked, and the remaining thing is that okay, the integration also we will try to have a look. Integration is also quite easy and it's not very difficult. That's the only thing left for us to discuss, I think, as per the schedule that we have. So continuity, finding maxima, minima, that's done. Higher order derivatives, finding integrals. Okay. So integration also we will just try to get an introduction into. So if there is any question to ask, you may please ask now. Otherwise, I will just try to show the integration related functions also. Okay. Okay, for finding the global maxima and global minima, we can say that once you find the local maxima, you can find the maximum values, and correspondingly, you can find the index of the maximum value you can locate, and corresponding to that, you can find out the global maximums. Okay, so that's how we have to find the global maximum. But I'm not going to that. If you can try it as an exercise, and I'm going into finding the integrals. So the command, the function for integration. So the function is 48. So 48 integration is here. The function for integration is once again coming from symbolic Python, from sympy import symbol, and then just like derivative integral. So once again, suppose we denote y equal to x equal to symbol x and try to evaluate it. Y equal to uh, let us take a simple function and try to integrate. Print integral of with respect to is, so three things. So there we put integral of y, okay, format y with respect to x, and integral y with respect to x, and as in the previous case we need to apply to it. That's it. So if you need to evaluate definite integral, then we need to specify not just x, but we need to specify the range also. That's it. Integral of with respect to from to. So let us see that what are this from and to. I don't know whether this will work here. Okay, it should probably work. Maybe I should evaluate that first, because otherwise the problem is that integral of yx, instead of that I am trying to substitute. Okay, so definite integral I will evaluate, because I don't know whether it will work. Directly putting the value here, it should work here. Okay, let me just try. 0 from where to where? from yx. So what is this? Integral of y with respect to x from 2, I should mention. So suppose that I take it from 0 to 2. So here also I should mention. That's only for printing. Here I should mention 0 to 2. Do it. Oh. So integral of x square with respect to x from 0 to 2, because it's x cubed by 3, it's 8 by 3. Evaluate. So all such functions can be evaluated, like the other functions like sin x from sympy import sine exponential. So print integral sin x with respect to x. Do it. And exponential x. So minus cos x and exponential x. So everything can be evaluated like this. Now, for finding the length of an arc, we know that for finding the length of the arc, we need to not actually for finding length of the arc. For finding the average of a function, we know that we need to integrate the function from one particular point to another particular point and divide it with the length of the interval. Okay, so that can be actually done. Finding now for finding length of the arc. Okay, so for finding length of the arc, we know that if the parametric equations are given as x of t, y of t, z of t, then for finding length of the arc, we need to integrate from t1 to t2 these functions, not these functions, t1 to t2 the norm of what you call r dash of t. R dash of t is nothing but x dash of t, y dash of t is a dash of t. Norm of that needs to be evaluated. So length of the arc can be found easily like that. For example, suppose that we have x is equal to, maybe I should define it as a symbol, and xt I will put. So t equal to symbol t. So xt, let me define it to be sine of t. Yt, define, oh sorry, yt, define it to be cos of t, and zt. These are just names equal to t. So now the arc length is print length of arc given by these three. Given by these three is maybe from 2 is. So what are the things that we need to give here? So we need derivative also. From sympy import derivative. So let us find r dash t or r dt, let me call it, because this parametric equations needs to be differentiated, and arc length is square root of x dash t plus x dash t square plus y dash t square plus z dash t. Okay, so for arc length, r dt, so norm is essentially that we are taking. Okay, instead of that, x dash t, x dt is nothing but derivative of x of t with respect to t, and do it. Similarly, we can find y of t So similarly, we can find z of t. So all these are found. Now a equal to, say, suppose that we are trying to find the arc length between 0 to 2 or 0 to pi. So pi is required. Pi, I hope that it's there. Pi is there. So now finding all these things. The length of the arc, xt, yt, zt. So from A to B is nothing but integrate. So what to integrate? Xt square. Okay, xt square needs to be integrated. X, not xt square. X dt square plus y dt square plus z dt square. That needs to be evaluated. That needs to be integrated with respect to t within the range A to B. Evaluated. Do it. But no, square root is also required. Uh, so integrate square root of this. I don't know whether this will work. Let me try. Integrate, not integrate, integral, sorry. It seems to be square root of 2 into pi. I don't know whether it's correct or not. Must be correct if I have done everything correctly. So let me just update the entire Google document with this. And with this, I'm probably stopping because I have almost reached the end of the session time. So this is a new file, updated the entire thing in Google document. You may try with your own examples, and this is, I think, the one of the things that we were included in the workshop schedule of items to discuss. Finding length of the arc and area between the curves is also there. That will take up probably tomorrow. So with this, probably I will stop. And if there are any questions, clarifications required, I can try to do that. Otherwise, I'm stopping. Thank you very much for your patient listening. Thank you.
Then or not, I think. So today's class was on how to find derivative or ordinary derivative, partial derivatives, local maximum, local minimum, point of inflation, plotting of critical points, etc. Thank you, Professor Vishnu Nambudiri, for making this session a very interesting by including many examples. Thank you once again, and I thank all the participants for the active participation. Today, so we wind up this program today, and tomorrow we meet at 6 p.m. Okay. Thank you all once again.
Thank you,
Good
ma'am.
night.
Thank you, everyone.